Hello class, welcome to this video on the 12.1 practice. So we have 3 questions that we want to go over for the homework assignment, starting with number 1. Kellogg's Fruit Loops cereal comes in 6 colors: orange, yellow, purple, red, blue, and green. Charisse randomly selected 120 loops and noted the color of each. Here are her data. Do these data provide convincing evidence at the 5% significance level that Kellogg's Fruit Loops do not contain an equal proportion of each color? Okay, so let's go ahead and basically they're asking us to do a significance test. We got our alpha 0.05. Let's go ahead and start our 4-step process. So it's starting with the state. So what are our hypotheses? So HO and HA. So we are going to try to instead of doing multiple tests here, we're going to do one test for goodness of fit, the chi-square. Right, so that means we're gonna say, okay, well, we're gonna say that the Fruit Loops contain an equal proportion of each color. You can say that the distribution of Fruit Loops is uniformly distributed, that kind of stuff. You can say that P1, P orange equals P yellow equals P purple, all that stuff. You can, and that they're all equal. So we're gonna say that we're gonna put this in words, and we're gonna say that the Fruit Loops contain an equal proportion of each color. All right, and then we're going to say the HA is that it's not, right? The Fruit Loops do not contain an equal proportion of each color. So notice that the HA is saying that it's not saying that all the proportions are different. It's just saying that they're not all equal, right? So that there might be some that are not equal, and that would still qualify as evidence for HA. Okay. All right. So then we're going to state that alpha is 0.05, and then we're going to go ahead and do our plan. So our plan of action. We're going to do a chi-square test for goodness of fit. All right, so let's do the conditions, starting with the random condition. Do we have a random sample? Yes. She randomly selected random sample of Fruit Loops. All right, and then next one, 10%. Is the sample 120 less than 10% of all Fruit Loops? We can safely say so, yes. We can say that 120 is less than 10% of all Fruit Loops. Okay, all right, and then let's do the large count. Remember that the expected count has to be all greater than or equal to 5, okay? So all expected counts. Now, is that true? Well, it is going to be true because we have 120 Fruit Loops that we selected, and each of them should have their 6 colors, so 1/6 chance, right? So 120 divided by 6, we would expect 20 Fruit Loops per, or 20 of each color, right? Which is all greater than or equal to 5. All right, so that's good. So we can do so now let's do the test. So we need to calculate our chi-square and our DF. Now we can use the chi-square goodness of fit test, in which case you can just write down your chi-square and your DF. But again, for the homework, I'm trying to emphasize knowing how to do the calculation, all right? Not just doing the test, not just, easy calculator and then do the test done. I want you to actually, do the calculation, okay, for the homework. All right, so so in this case, let's go ahead and do the chi-square. So now remember, we got DF is equal to 6 colors, so 6 minus 1 is equal to 5. Let's calculate our chi-square. So chi squared equals remember it's the sum of observed minus expected squared divided by expected, right? So that's the formula. So what did we observe? We observed 28 orange minus the expected of 20. Squared divided by the expected. And we expect all of them to be 20, so the denominators for all of these are going to be 20. And then we got observed for yellow, 21 minus 20 squared by 20. And you could do dot, dot, dot here at this point. So you can do dot, 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 and then finish with the last one if you want to save some space. Then the last one is 16. So 16 minus 20 squared over 20. Okay. All right. And we'll test this. You should get 7.9, but we can test it. We'll show you how to do it on the calculator in a second. So we can do the chi-squared GOF test. All right, so first I'm gonna do, well, let me put this off to the side. So chi-squared goodness of fit test. Calculator. We can do that in a second, but first, before we do that, I'm gonna draw the curve. And this curve starts out at 0. This is the chi-square value here, chi-squared axis, and we got the df equals 5, right, for this graph. So that means this is at 3 right here, the mode. And we're going to label ours 7.9. So 7.9 is not that far from here. 7.9 is like right here. We're going to shade to the right. And that's our p-value. Okay, and we're going to calculate the p-value in a couple of ways. We're going to show you how to do it using the table where the p-value is between two numbers. And we're also going to do it with the normal CDF, the chi-square of CDF. All right, so we got df is 5, and then chi-square is 7.9. So df is 5, chi-square is 7.9. So 7.9 is between these two. And so it's between 0.15 and 0.20. So it's a pretty high p-value, between 0.15 and 0.20. So table C. All right, and then using the calculator, we're going to use the normal CDF. Or not normal CDF, I'm sorry, it's chi-squared CDF. Our lower is 7.9. Our upper is infinity, so I'm going to just put 10,000. And our DF is 5. All right, and you should get a p-value about 0.1618. Now, if you did the chi-square goodness of fit test on the calculator, we would get chi-square. We would get a chi-square 7.9, and we would get a p-value of 0.1618. Okay, this is about the same as well. So we're going to show you both of these just to kind of see both, just to see how they compare. Okay, so we're going to go ahead and show you this. So we got, okay, so let's go ahead and do the chi-squared CDF. So we're going to do, we're going to hit stat. You don't have to hit second, just stat. And then go to, well, actually, no, we're going to do the chi-square CDF. So we're going to do second vars, and that's how you access the chi-square CDF. Not PDF, CDF, right? So chi-squared CDF, and then we had 7.9. 10,000, and then df is 5. All right, 0.1618, good. Now let's do the test. So stat, and then tests, go down to option D for goodness of fit test. Oh, and actually, yeah, the goodness of fit test, that's right. We need the data for that. So we're going to have to edit the L1 and L2. So let me quit out of that second mode. And then let's go back to stat and let's edit the list here. So we're going to get rid of these. No, there were, let's go to the observed. So the observed was, we got 28 orange, 21 yellow, so on and so forth, 16 purple, 25 red, 14 blue, and 16 green. And they should, we expect all of them, oops, just say 16 green. And I think the calculator replaced this with 20. Okay, so let me replace that with 28. Sorry about that. All right, so let's double check those numbers. That looks good. And then our expected was 20 for all of them. So I'll just double checking, make sure that that's correct. All right, and then we can go back to our stat and then go to our test. Okay, L1, L2, DF is 5. We can calculate. We get 7.9 for our chi-squared. That's what we had, and then 0.1618. So there you go. Okay, so there you go. So now we can go ahead and conclude. All right, so now because p-value 0.1618 is greater than our alpha, which we said was 0.05, we fail to reject the null hypothesis. That's the first part of the conclusion. Then the second part, we have to say whether we have convincing evidence for HA or not. Okay, so we do not, or we don't have convincing evidence for HA, which HA is that the Fruit Loops do not contain equal proportion of each color. Okay, so we just don't have enough evidence to support that it's different, okay, from our data. All right, so I got a second one here. All right, so biologists wish to mate pairs of fruit flies having genetic makeup, indicating that each one has a dominant gene R and then one recessive gene R for eye color. All right, so in this case, whether they have red eyes, dominant, or, here recessive. And having recessive for the red eye gene, or for that recessive gene, having both would make it white eyes instead of red eyes. And then you have a dominant along with one dominant and one recessive for wing type. So again, straight wings versus if they have curly wings, recessive being the curly. Each offspring will receive one gene for each of the two traits from each parent. So the biologists predict that the following phenotypes would occur in a ratio of 9:3:1. Okay, so there you go. So this is based off of Mendelian genetics. Assuming that the conditions of the inference are met, carry out a test at the alpha equals 0.05 significance level of the proposed genetic model. All right, so let's go ahead and do the state here. We're going to do a chi-squared test for goodness of fit instead of doing a multiple tests for each of these, right? We're just doing one test. So let's do HO and HA. So what are we trying to do? So we're trying to carry out a test for the proposed genetic model, so the 9-3-3-1 model. And so we're assuming that 9-3-3-1 model is correct, meaning that these proportions are in that ratio 9-3-3-1. Okay, so we're going to say the proposed 9-3-3-1 genetic model is correct. And then we're going to say that it's not correct on the flip side, right? Okay, so there you go. And then we're going to propose alpha is 0.05 because they mentioned that. All right, so then let's go ahead and state our plan. So we're going to do a chi-squared. You can say that. You can say chi-squared test for goodness of fit. All right. Okay, so there you go. So then let's go ahead and do the conditions. Well, actually, it says here, assume that the conditions of inference have been met. So we're going to assume that that's been met, okay? But I'm going to list them out so that you can remember, okay? So random, assume random selection of, these are fruit flies, yep. Assume random selection of fruit flies. All right, here we got, how many fruit flies did we get? Okay, so if we add these up, we got 200 for the total. Okay, so assume that 200 is less than 10% of all fruit flies. And then we got the large counts. Assume all expected counts greater than or equal to 5. All right, now they told us to assume that in the question, but I'm gonna treat this as if we have to figure that out, okay? So it says assume, but I'm also gonna list the counts so that we can find them. Okay, so I'm gonna show you how to do this. So if it's a 9:3:1 ratio, let me write it here, 9:3:1, add these up, 9 plus 3 plus 3 plus 1, that's total 16 parts, okay? So if we have 200 people, then this is going to be, if we had 200 flies, then the expected, this is the observed row, but the expected is going to be 200 times, we had 200 flies in total. Now, how many do we expect to be red eyes and straight wings? Well, according to this ratio, it should be 9/16 of the 200. Because it's if I add 9 plus 3 plus 3 plus 1, that's 16 parts, and 9 of those parts have to be on the first one. So 9/16 of the total. And then on the here, it's going to be 200 times 9/16 is 11.5. So 200 times 9/16 is 112.5, which is greater than 5. And then we'll do the next one. This is 200 times 3/16, right? 200 times 3/16. This 3/16 because now we're in the 3 part and the 3 part there. And then this one is 200 times 1/16 because now we're at the 1 part, 9:3:1 ratio, right? So 200 times 3/16 is 37.5. Greater than or equal to 5. And the last one is 200 times 1/16, that's just 12.5. Okay, so I know they said to assume, but I wanted to show you how you would do that if they give you a question like that on the test, okay? So it passes. All these are greater than or equal to 5. All right, so let's do the do. Again, you can type it into the calculator, but I do want you to practice doing the calculation, okay? So DF, we got 4 categories minus 1, so the DF is 3. Now let's calculate the chi-square. The chi-square, there's only 4 categories. So we got 99 minus 112.5 for the red eyes and straight wings. Square divided by 112.5 plus, we got 42 minus 37.5 squared divided by 112.5. And for the white eyes, straight wings, 49 And the last one, 10. So 10, and then we expected them to be 12.5. Oops, I put 12.5. I'm sorry about that. I need to fix that. This is the expected 37.5. They're different. These two are the same, but the first and last are different. Sorry about that. All right, so there you go, and we can calculate that. So when we calculate that, we should get approximately 1.469, around there. And we'll do this on the calculator just to verify that. And if we did the chi-squared CDF, our lower is 1.469, our upper is 10,000, our DF is 3. And again, we're going to do a chi-squared distribution just so that we can practice that. Our DF is 3, which means that this has to be 1. And then we got 1.469, which is right here, is really close to that mode right there. So we got a good chunk of the curve here. If we use table C, like I'm saying, I'm trying to go based off of the notes, so we're going over every single part of it. 1.469, and then DF is 3. Okay, so 1.469, DF is only 3. 1.469, notice that that is less than 4.11, right? So if it's less than 4.11, that means it's beyond, it's to the left of that, which means it's beyond 0.25. That means the p-value must be greater than 0.25, okay? Which we would expect it to be large based on what we see. And we're going to find out what it is. If we calculate this, we should get a large p-value, 0.6895 for the p-value. And if we used a chi-squared goodness fit test on the calculator, we would have to report our chi-squared. We'd have to report our DF, right? All that stuff. We have to make sure we report. And then it is 3. Okay, so this is what you would do in the do stage if you're doing it on the calculator. All right, but again, I want you to practice this whole thing. Doing this calculation, all that facilitates it in memory. So you know how you calculate it and you appreciate it and you know how it works, okay, rather than just relying on the calculator. All right, so then we got the conclude. We can conclude now because we got the p-value. We are definitely going to fail to reject because the p-value is large. All right, so the p-value, well, I forgot to do, let me just write it out, because the p-value uh, 0.6895 is greater than my alpha, we fail to reject HO. There is not convincing evidence that the proposed 9331 genetic model is not correct. So we don't have enough evidence to reject or to say that it's not correct, right? Based on the data that we have. In fact, it looks pretty good considering that the chi-square is very small. All right, so let's look at number 3, last one. Do seagulls show a preference where they land? To answer this question, biologists conducted a study in an enclosed outdoor space with a piece of shore whose area was made up of 56% sand, 29% mud, and 15% rocks. The biologists chose 200 seagulls at random. Each seagull was released into the outdoor space on its own and observed until it landed somewhere on the piece of shore. In all, 128 seagulls landed on the sand, 61 landed in the mud, and 11 landed on the rocks. Do these data provide convincing evidence that seagulls show a preference for where they land? I would suggest trying to do this question and all the steps prior to looking at the solution, just to make sure you're on the right track to get feedback. All right, so hopefully you gave it a try, you gave it a shot. So let's do the state. All right, so remember, do these data provide convincing evidence that seagulls show a preference for where they land? So the HO assumes that there's no preference where they land, meaning that it doesn't matter whether it's land, mud, or if it's sand, mud, or rocks, the proportion is going to be the same everywhere. So like the proportion in sand is going to be the same percent. Proportion in mud should be the same. Proportion in rock should be the same. That's what the HO is assuming, okay? So then the HO, we're going to say the seagulls do not have a preference, okay? So and the HO says that the proportions are different in each part, which means that there is, a preference, right? So the seagulls do have a preference. For where they land. All right, and then of course we're going to do our alpha. We're going to say alpha is 0.05, and then we'll go ahead and move to our plan. All right, so our plan, we're going to do a chi-squared test, right? That's what we said. Oops, let me undo that real quick. All right, we got a chi-squared test for goodness of fit. All right, so let's do the random condition. Do we have a random sample here? It says the biologist chose 200 seagulls at random. There you go. It says right there. Okay, so 200 seagulls at random. Okay, so we're going to say that. So random sample of 200 seagulls. All right, and then the 10% condition, we're going to assume 200 is less than 10% of all seagulls, right? That's a pretty reasonable assumption. And then the large counts condition. So now we need to do the what the expected values, right? So let's go ahead and do that. Now let's go ahead and emphasize this again. It says that we have an outdoor space and 56% of it is sand, right? So most of the outdoor space is sand. And if the null hypothesis is true that they do not have a preference, well then if I have 200 seagulls at random, if I have 200 seagulls, then that means that 56% of the seagulls have to be in the sand, right? If the null hypothesis is true. But if they do have a preference for sand, then that means we would expect for them to be more than 56% of the seagulls in sand. Does that make sense? So maybe we would expect 70% of the seagulls or more, or greater than 56%, right? That prefer sand, and less than the others. So this is what we're saying. So that we would expect that 56% of the 200. So let's do that here. So we're going to do, for the expected counts, we got, so let's do the expected. For, we have 56%, 0.56 of 200 is 112 seagulls. Then we got, so this is greater than or equal to 5, right? So that's good. Now let's do the other one. The other one was 29% mud. That's 58, which is greater than or equal to 5. And then the last one is 15% rocks. That should be 30, which is greater than or equal to 5. So all the observed counts are greater than 5. So check, okay? So we're good with that. Expected counts, and we have to mention that these are expected counts, right? Not observed. The expected counts, which is why I'm labeling them. All right, so we're good. So I'm just going to put it just to be clear. All expected counts greater than or equal to 5. All right. So now so we're good on that. Now let's calculate the chi-squared. Sorry about that. Let me move that back. Sometimes the page slides. All right, so we got chi-squared is, now let's do the thing. So 112 is expected. What did we observe? We observed 61 or 128 on the sand. Okay, so 128 is on the sand, but we observed, or we expected 112. It says we observed 61 in the mud, and we expected 58. All right, we observed 11 in the rocks, and we expected 30. That looks like a pretty significant difference, right? That's going to impact our chi-square for sure. All right, so let's calculate that. So if we do that, we would get, let's actually write these down. I'm going to write each of these down. So the first one is about 2.286. Second one, 0.155. Next one is 12.033. Look at that. That's what we're talking about. That's a big difference with the rocks. They do not like the rocks. We observed 11, and we expected 30 of them to be in the rocks if they were the same, but they do not seem to like the rocks, it appears. So let's look at approximately, and if we add those up, we get about 14.474. And remember, our degree of freedom is, we had 3 categories of lands, so 3 minus 1. All right, so there's our DF. And let me do all the usual stuff. Zero there. And then DF is 2. Now the DF is 2. Actually, if DF is 2, it doesn't even look like that. DF is 2, because remember then, yeah, so the DF being 2 is going to look kind of like this. How do I know that? Because remember, if the DF is 2, then the mode will be 2 minus 2 is 0. We can't have the mode being at 0 because, yeah, we can't have the mode being at 0. It would be kind of weird, and then having an average. So what it's gonna look like is that for it to have the highest peak at 0, it would have to go like, you know, it would have to peak at there and then go like that. Okay, so it'd have to look like something like that. But of course, it's going to be more curved. But not that you had to know that or draw that or anything. You know, you can draw it when you do your chi-square goodness of fit test. You can draw it and actually see how it looks like. But there you go. So now you can we can label the chi-squared as 14.474. Shade to the right, and then we'll find the p-value. So if you so we'll do the normal, we'll do the chi-squared CDF. You don't have to put the dash there. I'm used to putting the dash. Chi-squared CDF. Lower is 14.474. Upper is big number, 10,000. DF is 2. So if you calculate that, about 0.007 around there. There you go, really small, 0.0007. All right, and again, you did the chi-square goodness of fit test, you would get the same thing. You would have to report the chi-squared value, the df, and then the p-value. Let me put that, that's my p-value. All right, so now we can go ahead and do the conclude stage. We can see that we have significant evidence. We have convincing evidence here because p-value of 0.0007 is much less than alpha 0.05. We reject HO. There is convincing evidence for HA, right? And what was HA? Well, there was HA assumed that they do have a preference for where they land. So there's convincing evidence for, or we could say that seagulls do have a preference for where they land. So then part B, it says relative to the proportion of each ground type on the shore, which type of ground do the seagulls seem to prefer the most and the least? Okay, well, because we already know the chi-squared values, if you look at the chi-squared values, right, it was 2.286, 0.155, right? This was the sand, this was the mud, and this was the rocks. So you can see that the biggest contributor are sand and rocks, right? So relative to the proportion of each ground type. Okay, so now if you just look at the chi-squared, you would think, oh, well, this chi-square is bigger, so they prefer the rocks. But no, remember that the difference there was negative, right? So the for the rocks, it was, if you recall, 11 minus 30, which was negative 19. So we have a 19 drop, right? So relative to the total to either the proportion of each ground type, that's 19 out of 30. That's a good chunk right there. And then for the sand, it was 128 minus 112, or plus 16. So look at that, plus 16 there versus negative 19. So you can see that they prefer, they appear to prefer sand the most and rocks least. And let's see, we're going to plug this data in and see how it looks like on the calculator to see the contributing part. So we can kind of show you that aspect of things as well. All right, so let's do the goodness of fit test. So we're going to go to stat. Well, first we got to, stat, and we're going to edit. So we're going to edit our list. So we can delete these numbers and we can do our preferences. So there's 3 regions, right? So here we had the observed, so 128 observed, 61 observed to land on mud, and only 11 landed on rocks. And we expected 112 to land in the sand. We expected 58, and we expected 30 here. Yeah, so big difference in the sand and in the rocks. And then let's go do the test. So stat, tests, go to goodness of fit test. And L1, L2, our degree of freedom is 3. Let's calculate. If we were to draw this, let me just draw it real quick. You can see, okay, it's really tiny portion here and then like that. So again, it's a little bit different from what I drew, but you can see that right here is, where it should sort of look something like that. But it's very sharp. But anyways, that's just, I was just curious about that. So we got, just go back. And then let's do df is 3. Let's calculate. All right, there you go. So we got the p-value, really small. We got the chi-square. Now look at the contributions. 2.28, that's what we had for the contribution, if you recall, 2.286. We had 0.155, that's what we had for the contribution. 12.033, that's what we had. So you can use this to determine what the contribution is for the specific terms in the chi-square. So it's really good if you want to test out the specific terms to see if you got that, okay? All right, I just wanted to show you that. All right, guys, that's going to do it for the video. I hope you found this useful and informative. And as usual, I'll see you in the next one.